there any really big questions on the homework, I can try and answer them for a couple minutes now as well. I mean, some of you to be a bit of a challenge. There is not going to be, if you complete what I asked you to complete, I'm not going to penalize you for if it takes longer. All right, so don't worry about the actual runtime. You know, as long as it's finished, it won't affect the grade. If it's faster, that's also great. I encourage you to try and make it efficient. But there's not going to lose points over that. And if you can't quite finish everything, you might lose a couple points, but not too many if you can't quite implementation quite fast. All right, so I'll talk more about the proposal on Wednesday as well. So start thinking about that. Yeah.
Just a question about the homework. So for plotting the runtime, we had to test 3 different parameters for the trials, the number of trials. Should we have that like the same plot, like 3 curves in the same plot or same graph?
So that would be a great way of showing it. I, on purpose, did not tell you exactly how to plot it and to show this because I want you to think a little bit about these things. And I've gotten good questions about that. That's good that it's not obvious, but you had to think about the right way to do it. Because if you're on the job, no one's going to tell you, okay, give me this many lines on this plot like this. You're going to have to make wise decisions. So shouldn't be too hard to figure it out, but yeah, that's a great way to think about it. All right. Oh, question.
Problem 3, when you have to compare like the analytical and experimental trials, should on part B, should the analytical be higher or lower than our experimental?
So it should be about the same. I don't know whether it will be exactly higher or lower. The point of asking a question like this, and a point of a lot of the mathematics I'll end up doing the course, well, it's not the only point, but one of the points, is because we'll be doing these randomized kind of analysis or randomized algorithms, and it's hard to check whether you're doing it correctly or not, right? So I want this to serve as kind of a check against your algorithm, and the main point is that if it's way off by more than an order of 2, you're probably doing something wrong. Okay, either in the analysis or in the code, and you'll have to figure out which one of those it is. And this is a common thing that comes up, and so I don't know what the, you know, and again, it will depend on which of the analyses you use. I think I mentioned, I think this one should be pretty, the expected value for point B, we calculate the exact expected value, so that one should be right in expectation, and that one's fairly well concentrated. But it could be on either side. So I think it should, in expectation, be right on. But for what your results actually see, it might be one way or the other. And that doesn't mean it's wrong if it's a little bit off, right? It's not going to be exactly the right answer, but it'll be in the right ballpark.
What would the margin be for the ballpark?
So I'm not sure offhand what it is, but if you want to get a sense of if you're getting the right margin, rerun your experimental stuff and see if it's always less than. And if it's always less than, then you have something off. If it's something sometimes less than, sometimes greater than, then that seems reasonable. Yeah. If you're really concerned, maybe we can work through the actual kind of some variance calculation a little bit later. But other stuff planned for this lecture. So great. So those were great questions. So that's, I think you're really getting to some of the hidden points of this assignment. All right. So oh yeah. So hopefully our new video recording equipment is working, and hopefully we're now live streaming class. This is the first, hopefully, effective live trial of what's going on here. But apparently the Wi-Fi is sketchy in a lot of the engineering part of the campus today. So again, can't guarantee everything will work as planned. So great. So today we're going to talk about what's called the main points will be the Jaccard similarity and doing Keygrams on text. So the basic premise of what's going on is you're going to start with some messy input data, and this could be something like so homework assignments. It could be something like web pages, or like some or like some collection of emails. So for homework assignments, I might want to know whether you know, 2 homework assignments are one is likely is a copy or plagiarism of the other one, or maybe nearly a plagiarism with a few things changed. With web pages, Google wants to know the same thing. It doesn't want to show you essentially 5 copies of essentially the same web page in the top 10 list. They want them they want all of these to be diverse. And with emails, spam email is often, you get the same message sent out over and over again. And if you ever notice that sometimes you'll get a spam email and it will have weird misspellings in it. So we'll see why those weird misspellings are in there. That's to try and fight against these detection of if it's like the same email you've seen before or nearly the same email. They'll try and put in just enough typos so you can, not too many that you can't still read it, but enough that it can't get by the spam filters. So the problem is, I want to take, let's say, 2 of these homework assignments, H1 and H2, and I want to determine, you know, and so I wanted to find a similarity function between H1 and H2 and ask, is the similarity of H1, H2, is this large? If the similarity is large, then it means they might be essentially copies of each other. All right, so like, if I'm just given the homework assignments or just the web pages or just the emails, this seems like kind of a task that involves a lot of domain knowledge about what's going on here. But we'll see a common abstraction, which is kind of the bulk of what most of these things use. Okay, they may add on various other elements to this, but we'll see the bulk and the majority, or maybe the entirety of what the similarity function is, will be some of the things that we that we're seeing today. Okay, and so the first basic step is to model all of these into just a string of text, right? So it's going to be just a string of words and text. And so there could be like plots and so forth in the homework assignment, or there could be like there's other HTML code and CSS files in the web pages, and the emails, there are headers and stuff like that. But we're just going to look at the text for now. Okay? Some stuff later on in the semester, we'll see how to kind of add on some of these other elements, in some ways in structured ways, and other ways kind of more ad hoc things we can do. But we're just going to look at the text now. So we're going to model any homework assignment or a web page or email just as the text that's contained in it. Okay? Now, it's still not clear how, if you have 2 pieces of text, how do you say how similar are those 2 pieces of text? And so we're going to look at a way to convert this text into one of 2 different abstract kind of representations. The first one we'll talk about more briefly is to a vector in RD. So this is going to be a set of d-dimensional real numbers, right? So a vector would be v1, v2. So we have some vector v, v3, up to VD, right? So I'm going to have D scalar values, okay? And when I have it in these, so where it's comma separated so with parentheses, this means it's going to be a vector, and I'll say that this vector lies in RD. And so the R just means it's kind of a scalar value. It could be continuous. You can think of it like a double, essentially. We might restrict this more to be binary or something else at some other point. Okay, but the order of these matters. If I swap V2 and V3, this is a different vector. Okay, and so if you have a vector, the common distance between two vectors. Let's just do a simple example here. So I have an x coordinate and a y coordinate, and I'm going to have A equals, let's say this is going to be 1, 3, and so then B here is going to be, what is this, 4, 2, and then the simplest distance is the Euclidean distance between them, which I'm going to call, so I'll write this, I guess, as DE between A and B, or equal to A, B, 2. And we'll talk about this notation much more in a week or so. But it's just this, you can plot the vectors, and then it's a straight line, the length of the straight line distance between them. Hopefully you've all seen Euclidean distance before. We'll talk much more about this and a bunch of variants of this later on in the semester. Okay, so one way is this vector representation, and this is pretty, once you get it, it's pretty intuitive how you measure the distance. The other thing we'll talk about is to, instead of representing it as a vector, we're going to represent the text as a set. So most of the lecture today we'll be talking about this set representation and the distances or similarities between sets. Right? So the set is a little bit kind of messier notion to think of, but there's, so any set is going to be an object S in some sort of domain, right? And this domain might be something, for instance, you could have an example, this domain is going to be, it could just be this abstract representation we talked about last Wednesday, where it's a set of n objects and I've labeled them by the integers, right? But we'll see something a little bit more tangible when we talk about these sets. Now, the implementation might think of it this way, but we'll talk about them more tangibly. So then a set S might, an example might be 1, 7, 14. And these are just 3 elements of the set. And I have a curly bracket now, still separated by commas. Now the ordering does not matter. If I swap 7 and 14 in this representation, this is equal to, for instance, 1, 14, 7. And I can even put a 1 here. I probably wouldn't put this 1. This is equivalent. I don't count the number of times. I just count which distinct elements. So I would probably not even write this extra 1 here. I would. So the ordering doesn't matter, and it doesn't count things twice. I just see if it's present or not. Okay. All right. So how do we talk about? Okay. So let me. I've mentioned 2 things now. I've mentioned these sets, and I've mentioned the Euclidean distance. Oh, sorry, not sets and distance. So I'm going to talk about, I mentioned the word similarity and distance. Okay, so with sets, it turns out it's much more natural to talk about similarities instead of distances. And with vectors, it's easier often to talk about distances, but we'll go back and forth between these. And so, just so it's clear what's going on, if you have, so often I'll write a similarity between 2 objects as A and B, and a distance as some form of of something like this. So if if this is small, then A and B are far away from each other in a concept. But in a distance, it means A and B are close. So these are kind of opposites of each other. If something is very similar, that means it has a high similarity value, right? But that would mean its distance is small, right? So think of these are kind of like inverses of each other. So this is usually 0 means the same. And so in the distances, sometimes 1 means the same. This will be, so for some of the distances that we use which are derived by sets, this will be true. In Euclidean distance, it'll be like, right, so usually, usually 1 means the same, and here's, and yeah, I've got this backwards. Transpose my notes for my up here. So so in the distance, 0 means the same, and usually distance 0 means the same, and usually 1 means the same in the similarity. On the other side, this is usually S is going to be in between 0 and 1, and a distance will usually be between 0 and infinity. So there'll be, as I mentioned, there'll be some distances we'll see derived from sets where the maximum value will be 1. That's perfectly going to be perfectly fine. It'll still be what's called a metric, which we'll talk about later in the semester. Okay. You can often convert between them as the distance between A and B is equal to 1 minus the similarity between A and B. But this isn't the only way to convert between them. In some cases, it'll be better to do the distance between A and B equals something more complex, which is similarity between A and A plus similarity between B and B minus 2 times the similarity between A and B, all under the square root. Okay, so it depends on how, it'll usually one of these two forms. Okay, so for most of this lecture, it will be this form. But when you think of Euclidean distance, its analog to a similarity is actually going to be the dot product between the two vectors, and which we'll talk about later on. And the dot product will, if you put it in here, you will recover the Euclidean distance.
So if the distance is the set of all numbers, of all positive numbers to infinity, 1 minus numbers bounded on 0 to 1 would be a number between 0 and 1, right?
Yeah, so if I'm deriving a distance from a set, right, then I'm going to start with my set in this form, and then the distance will be between 0 and 1. Right? Now, that satisfies this still. It's just I never am above 1. Right? If I'm talking about something like Euclidean distance, right, then the two vectors can be infinitely far apart. And actually, if I use the dot product between them, then this will actually recover Euclidean distance. And that's also fine. In that case, the dot product could also be infinitely large. So, but it's a similarity in this sense, but it's kind of it's less standard to talk about that as a similarity because it's not bounded. It's less clear of when things are the same. And we'll get back to this issue more in a couple lectures. We'll talk about the cosine similarity, which is kind of a restriction of the dot product, which fits this closer to this form. Great. Right, so there are lots of versions of similarities and distances and kind of how to convert between them. This is the first time I'll mention this, but it won't be the last in this class. Okay. Okay, so the main similarity we'll talk about is going to be the Jaccard similarity. Okay. And so this is going to be defined, it's going to be defined between two sets. Okay, and so I'll use a running example where the first set is 0, 1, 2, 5, 6, and B is going to be 0, 2, 3, 5, 7, 9. Okay, so I've just given them, the elements are just integers for now. We'll make something more tangible in maybe 10 minutes or so. But they're just integers for now, and I did not need to define what domain these sets are over, it turns out. And we'll come back to that point. All right, but if you're confused about that, say they're integers between 0 and 9 or 0 and 10, turns out it's not going to matter. Now, the Jaccard similarity, A and B, is now going to be defined as A intersection, the size of A intersection B divided by A union B. Okay, so when I write these vertical bars here mean the cardinality or the size of the set. Okay, so when I put those vertical bars like that, and those should be single vertical bars, I redrew them in blue to highlight them. That's the size of the set, right? And hopefully you know what the intersection is, just as a, to go through this example. The intersection, the things which are in both, is going to be 0, 2, 5, and I think that's it. And the union is the things which are in either 1, 2, 3, 5, 6, 7, 9. And so the sizes of these are 3 over 8. Okay, so the Jaccard similarity is 3/8, right? So this is 0.375. Okay, so this is the Jaccard similarity on these two sets. So it's pretty simple to define. For any two sets, you can define this. In order to define this distance, I did not need to know all of the objects in the distance. In the domain which the elements are drawn from, I only need to know the union and the intersection of them. And in the lecture on Wednesday, we'll see why this is a really useful property to have. Not all set similarities have this property, but this one has this property. Okay. So if I were to add an object to A that was not in B, should they become more similar or less similar? It should probably become less similar because it's going to A and it's not in B. So if I added 4 into A, it should be less similar, and that will bear out. The numerator, the intersection is not growing, but the denominator, the union is. Right? So it would go from 3/8 to 3/9. Okay, if I added 3 into A, that was also in B, right? They should become more similar because their overlap is larger, right? So the denominator would go to 4, and the numerator would go to 4, and the denominator would stay the same, right? And so it would be 4/8 instead. So that would be more similar. And if I added something new into both of them, well, so if I added, let's say I added 4 into both of them, right? This could go either way, right? Maybe it's more similar, maybe it's less similar. I think in this case it will become more similar. I would increase the numerator and the denominator, so it'd be 4/9, which is bigger than 3/8. Okay, but that's not always the case. Okay, so if clearly the overlap as a percentage of the union is getting bigger, then they should become more similar, and that's what the Jaccard similarity is capturing. Okay, so this is probably the single most common similarity between sets, and you can define something, the Jaccard, or you write it this way, the Jaccard distance A, B is going to be 1 minus the Jaccard similarity between A and B. And so this will be what this turns out that this will be a metric. We'll discuss what that means in a week or so. Okay, but this turns out to be a nicely defined distance as well. So I can think of this as a distance, but it only goes between 0 and 1. Okay. Yeah, so, okay, I want to mention that there are many ways to find similarity. Okay, there are lots of ways to find similarities. To define them, I'm going to use I'm going to find 3 different operations. Let's do this up here. So A intersection B. I'm going to use A union B. It turns out I'll take the complement. I'll want to use the complement of A union B for a reason here, right? So I'm going to have some overall domain, omega. I'm going to have, this is A. I'm going to have color B. Okay, so you have A and B. The intersection is in between. The union is both of those circles. I haven't needed, and I take the complement of the union. Then the complement of the union here is all of this region out here. But I have to define this entire domain to do that. Okay, and then I'm going to use one more operation here called the the symmetric difference. The symmetric difference between sets A and B, and this is going to be the things that are in either A or B, but not in both. Okay, so the symmetric difference is going to be this region. It's in A but not in B, or it's in B but it's not in A. Okay. So I'm going to use. So I'm going to define a class of similarities which will be kind of fairly nicely behaved. That's going to kind of make sense. And this generality is from kind of some research which shows like all the sets of similarities which can be used for some of the downstream things. The algorithmic tools will be used we'll see over the next week or two. And so it's going to look a little complex, but it's going to capture kind of a broad class of similarities, and all of these should roughly make sense. Okay, so I'm looking at the cardinality of each of these terms, and I'm going to put a parameter in front of these. So I'm going to define a general similarity, x, y, z, z prime between A and B is going to be x times the cardinality of A intersection B plus y times the cardinality of A union B, the complement of that, plus z times the cardinality of A symmetric difference of B. And I may set some of these parameters to 0. And then I'm going to divide this by x A intersection B plus y A union B complement cardinality plus z prime, so that's a different parameter than z, a symmetric difference of B. Okay, so it looks kind of complex, but this defines kind of a fairly general class. If I plug in any kind of positive or non-negative parameters for x, y, and z, then this will kind of make sense. It will turn out. So for instance, the Jaccard similarity is going to have parameters. You can do this with x equals 1, y equals 0, z equals 0, and z prime equals 1. Okay, so it's going to be a little bit strange. So on the top, I'm only going to have 1 times the cardinality of the intersection, right? That was the same as before. For for the bottom, I'm going to have 1 times the cardinality of the intersection plus 1 times the cardinality of the symmetric difference. I add those two together, that turns out it's the union, right? It's the unfilled picture in this kind of illustration up here plus the black section, right? That together is the union, right? So that recovers the Jaccard similarity, right? So you kind of need a couple extra parameters to capture kind of the broader class of things, which kind of generally makes sense. And there's some classification that if it doesn't fit this pattern, then it's either there's some way it's not going to make sense a it's not going to fit in one of the algorithmic tools we're going to use. So there's some rationale behind this complex formula. Okay, so I'm going to write down a few other similarities. There's something called the Hamming similarity between A and B. And this is equal to this general form 1, 1, 0, 1. And this will be equal to, after I simplified everything, 1 minus the symmetric difference of B divided by the size of the entire domain. Okay, so basically this is going to be the fraction of items which are the same. Okay, so if the symmetric difference over the domain, those are all the things which are different between each other. And this is commonly used. You can represent a set as a bit vector over all the possible elements, and it's the fraction of the bits which match in these bit vectors. So if object 1 is in the set, then the first, or object 7 is in the set, then the 7th bit is 1, otherwise it's 0. And it's the fraction of bits which match. Okay, and if you work through these numbers, you can see that you can recover this. So hopefully you've heard of the Hamming distance before, right? So the Hamming similarity is 1 minus the Hamming distance. Okay, so the Andberg similarity is going to be defined S1002. Okay, and so this one, simplified form, is A intersection B divided by A union B plus A symmetric difference of B. Okay, so this looks a lot like the Jaccard similarity, but I'm weighting the symmetric difference a bit more. So that's what I'm doing in the denominator. This still makes sense, and I've seen I'll mention only ones that I've seen used in research papers for some task or in some documentation for some task. Those are all used. Yeah.
So I just had a question on the Hamming one. It's 1101. Wouldn't that make x1, y1, and z, which is the symmetric difference, 0?
Right. So the last one is z prime. So the
denominator would include all of it. But the numerator, why is it the symmetric difference?
So I'm not including the symmetric difference in in the numerator.
Oh.
So z is on the numerator and z prime is in the denominator. Yeah. It's a little confusing. I took this notation from a paper. Maybe there's some better way to write this. Yeah. If you look at it a little bit, it's a little confusing, but it's not too hard to kind of do a little set algebra to figure these things out.
What's the difference between z and z prime?
Right. So if I look here, this is z, and this is z prime. Right. So they're showing up in different spots in this formula because they're both modifying the size of the symmetric difference. Okay, so they're kind of related in some way. There isn't any other reason than that, as far as I know. Okay, so there's another one. Similarity is S1102, and this simplifies to, let's see, the size of the domain minus the size of the symmetric difference divided by the size of the domain minus the size, plus the symmetric difference. Okay, so the numerator is always smaller than the denominator because this is a positive point. Right, and you can see maybe this seems reasonable, you know, it kind of makes sense. Again, as I increase the symmetric difference, then these become they become less similar to each other.
Symmetric difference. You define the z prime as 2, right?
Yeah, so I find the z prime as 2, but I need one of them to create the union because I'm adding the symmetric difference to the intersection. Right, in order to create the union, the y is for the complement of the union. Okay, so you can go and verify these things, that they're not too complicated. I just want to mention one more, just so you see the breadth of these things. And so none of these are too special. This one is going to be 2 times A intersection B divided by the size of A plus the size of B. Okay, this is the dice similarity or the Sorensen dice similarity. All of these are used and sometimes used. Okay, so the point of writing these up is not the specifics of any one of these. We'll study the Jaccard for the kind of, we'll use that as an example for most of the rest of the class. And that has the most historic value within kind of understanding, doing search on web pages and so forth. And in a lot of these cases I mentioned. But these are all reasonable choices of similarity, okay? So the point of writing all these up here, these are all well-formed. There's not a lot of differences in like one. You can't say one is strictly better than the other one. So whenever the first thing you do when you're trying to do some analysis of some data is you need to make some choice of similarity you're going to use, and it's going to be somewhat arbitrary. It's some modeling choice. There's some subtle differences between these, but those differences are not too important. There's some kind of domains where it makes sense to use one or the other. If by default I would use the Jaccard, it seems to be the most popular, but in some areas, kind of the dice or the Hamming or the Anberg is the default measure to use. And so that's what everyone uses when they do their comparisons. And so if you ask me what's the best one, I cannot tell you which is the best one. There isn't an answer to this. Okay? Okay, so I've listed these up here just to kind of infuriate you and confuse you a little bit, that I'm starting by giving you more questions than I'm giving you answers. Okay, but that's just the way it is. Okay, so the sooner you realize that, it's the better. Okay, and hopefully there's not a typo up here. There might be a typo.
I calculated, figured it out. So you basically split one and combine it with intersection.
Yeah.
You got the union. And then
Yeah, I skipped a bunch of simplification steps, and there's more detail in the notes. So, okay, all right. So let's try and use these. Let's use the Jaccard distance now. Come back to text and see how we can actually use the Jaccard similarity here. Okay, I started out by saying we have these object web pages, homework assignments, and we're going to boil them down to text, and then we're somehow going to use these set-based similarity functions. But I haven't connected these two together yet. So we somehow need to turn text into a set. I'm actually going to start as a warm-up and something which is probably a little bit more intuitive and convert it into a vector, which is also a fairly common thing to do. So the first thing we're going to do is we're going to convert this into a vector in a method called so called the bag of words here, the bag of words technique, and we're gonna use this example text here. So hopefully this is, maybe you've seen something similar to this before. I think in my book I changed it anymore. Dr. Seuss used to be fairly strict over copyright issues, so I didn't want to mess with that. But it's a nice simple example of 4 different documents. And so the first thing we're going to talk about is this bag of words model. And we're going to pretend that there are only, let's see, how many words do I have here? There are only going to be, I think, 12 possible words in the dictionary here, right? So am, and, do, eggs, green, ham, I, like, not, Sam, them, zebra. Okay? So these are the only possible words, and these represent coordinates of a 12-dimensional vector, right? So this is going to somehow represent our 12. Okay, so 12-dimensional vector, and so the bag of words technique is basically just these are going to count the number of each of these words. Right? I'm going to count in the first, there's one instance of the word am, right? So I'm going to get a 1. The and never occurs, so I get a 0. Let's see, this should be I, and this one should be Sam. Okay? The rest are zeros, right? Zebra I never use. So it's all zeros here. I think everything else I use at least once. So the longer sentences, the longer documents end up having more non-zero vectors in them. And if a word, this is the word I believe. This one occurred twice in this last document, so I put a 2 here. Okay, I think in the notes I said you might not count it twice. Usually you would count it twice in this representation. There's some instances where you won't, but in general you would. So I'm going to fix that in the lecture notes. Okay, so this is the bag of words representation. It gets me vectors. I can then take the Euclidean distance between these vectors. This kind of works. Okay, this is a good first approach to what's going on here. We'll see in like next week, I think, a better distance to use between these vectors. Okay, but if you want to get a first approximation of what to do with these documents, create these bag of word vectors. It's pretty straightforward, and then look at the Euclidean. We have a lot more words. These vectors are going to be much, much, much longer. Okay, that's okay, actually. There are a couple options. I mean, we can ignore some really rare words and some other issues. You know, that might be okay. Or we just keep around really, really large vectors. You might want to use a sparse format when storing them. Okay, think of it as a linked list between the non-zero objects. You can do that instead. And we'll talk more about those issues later in class. Okay, but what's more commonly used, this is starting to change the last kind of maybe 3 or 4 years. There have been other ways, much more powerful ways of dealing with text, but historically for like 20 years, the way people using things things like Keygrams, okay, sets. Okay, what a Keygram is going to do is it's going to kind of look at these consecutive sets of words that are strung together, right? So if I look at a K equals 3, then it means a group of 3 words together, and so to do like I do not would be one string of 3 words, right? And that string occurs both in the first and the second sentence. But I'm going to kind of overlap these, and so it's sometimes called shingling, like shingles on a roof, where the next one would be do not like. Okay, the do not will be in both, and then I'll have a not like green, and a like green eggs, and a green eggs and an eggs and ham. Right, so that would be for this document. Those would be this set of the 4 different Keygrams, or the 5 different Keygrams here.
And they have to be consecutive?
Yeah, so they meant they have to be consecutive. So think of it from a language perspective as capturing some of the local kind of behavior of the words. It's not just like, but it's not like. I've captured that I don't like something because the not is in front of the like. Right, so I don't like green. Not like green is what I'm capturing. Turns out it's actually green eggs and ham. Okay, so we can talk about some of these issues in a couple minutes once I give some more examples. Okay, so at k equals 1, I'm just capturing, and now I'm treating this. I I'm treating this as a single document in this example. This is for treating this as a, okay, just for now I'll treat this as a single document, and these are all, I only appears once because it's a set. I don't care how many times it occurs, just if it occurs. Okay, and if I do a 2 grams over the whole 4-line document, right, these are the grams I'm going to get. I am Sam, Sam, I go across the line. If you have a text document, you would typically do that. Sam, I, am I, but not I am. I already had here, so I only count it once. Okay, so if you have like a set representation inside of, don't worry too much about this detail, but it's a set, and that'll matter in the Jaccard. Some of the techniques we're going to use with the Jaccard similarity, if I were counting things twice, those techniques are actually not going to work. It's important for the techniques that I define this carefully as a set, not a multi-set. Yeah.
Is there any benefit for doing like a 1 gram and a 2 gram and 3 grams separately? Like, does it make sense? Like, I'm counting I am and separately I and am for each instance.
Yeah, you could do that. This, like, yeah, you could throw all of these into one large set. This would probably be fine. One issue with this is the 1 grams are going to be much more common because it's harder to match 2 words in a row than is 1 word in a row. It could be that most documents on kind of have the word the, right? So that's not going to be as interesting, right? This is known as a stop word, and there are a bunch of these singleton words which are very common, but there are other words which can be much more common as 1 grams. And so that might cause some weird thing in that being both of them in the same set.
Is this like k-means where you like apply different values of k to find out what the best one is for your problem?
Yeah, so you might want to try different choices. I plan to mention in a couple minutes, but this has been studied for a long time, and people have tried different values. And I think this document is too small for this technique to be effective. But for, say, documents on the web, like web pages, is probably going to be the most effective thing. Maybe 4, but yeah, probably not 4. That's probably too long. You may have a hard time finding similarities. If you're only doing a 1 gram, you're not getting much of the advantages, so you're probably better off doing bag of words instead. Okay. I want to mention that you can also do Keygrams with characters instead, and this is roughly as popular as doing it just with words. So now I'm going to treat 3 consecutive characters here. Right, so I'm going to get 3. So IAM, AMS, MSA, SAM, and so forth. Right. I'm only looking at just the character sets instead of the actual words. In some sense, it's if the characters are kind of capturing the words, because in order to have the word, I need to have all of those relevant character strings inside of it. But maybe if there's a misspelling, I'm still capturing a lot of what's going on. And I can capture some more nuanced things using the charactergrams. These are a little bit less intuitive to work with, and so that's, I think, more have been a hindrance of why people haven't used them as much. But they're just as common to use the charactergrams instead of the wordgrams. Okay, and so usually when a new technique for analyzing large-scale text appears, usually they first do it with wordgrams, and then later on someone does it with charactergrams instead, and maybe it might, if you tune everything right, it might be a slight improvement. There are these things in natural language processing which made a big kind of improvement over some of the things we'll talk at the end of this lecture just in the last few years, called Elmo and BERT these two different techniques, and Elmo came first, and I think this was wordgrams, and then there was, or something like wordgrams, and then BERT came out this year, and it uses charactergrams, and among other things, it changes, but it uses that, and it does slightly better. But these are kind of in kind of usually the last 5% of performance that you're squeezing out. Okay. All right. Okay. So we started asking about these things, but there were a bunch of questions you asked already. But I just want to highlight what were some of the modeling choices that we made, or that were implicitly made in the examples I did. And the first thing was the choice of K, right? And I also talked about word versus the character. Did I group things, shingle things based on the words or based on the characters? Right, but there was other kind of implicit modeling choices up there as well. So what other ones did you notice? I also made in those examples. Yep. So in the charactergrams, did I include spaces? Right. So if I go back here, I am Sam. Could have been a space between I am. So maybe the first one was I space A. That would be a reasonable thing to do. Maybe I want to distinguish between people who use two spaces after a period or one space after a period. And so I want to count if there are two spaces or something like that. Or there's a return at the end of a line. Maybe that matters, right? So how do I deal with the white space? Yeah, so I could have included it, or I can decide not to include it. In your homework, which is going to come out by Wednesday, we're kind of revising the last bits of it, and it will be due in a couple weeks after that. So, but I'll ask you to include white space in them, I think. I think that's what I do. Okay, all right, I'll do something like this. So it's important to figure out, are you going to do white space or not? Actually, no, I won't. I forget what I'll do, but maybe I'll still change it. So, okay. Well, what other modeling choices did I make, or could I have made?
Capitalization.
So capitalization, yeah. So I used the word Sam in the wordgrams, and I kept Sam capitalized there. In the charactergrams, I made everything as lowercase. Right, so the more distinct you can make things, the fewer matches you're going to get. Right, let's say that if something appears at the beginning of a sentence, it's going to be capitalized when it might not otherwise. And so maybe I want to distinguish that, maybe I don't. Right, these are differences I can pull.
You store your grams in a set and not a vector?
Sure. Okay. Yeah. So. Yeah, so the set versus vector is kind of, yeah, so this goes back to, if I use the vector, I'm probably going to want to use something, there's a different set of techniques based on Euclidean distance, and we'll see cosine distance and some other things which will be more natural for that, but yes, I made that choice as well. Yeah.
For a bag of words, you pick a dictionary. Is that, like, I mean, you added zebra to the dictionary and decided it was 12, so like,
yeah, so if I use the vector, then I need some dictionary. With the sets, I did not. Right? So that was a cute thing about the sets. Turns out with the vectors, and we'll see this not till the middle of the semester, but there's a way to get around using a dictionary effectively with vectors that most people use. Yeah, so that turns out it doesn't matter. I'm just storing them in some sort of set representation. So think of it as a set data structure, and it stores them however it's optimized and is convenient for it. It doesn't know the order within them.
Ignore punctuation.
Yeah, so I did not include punctuation. Okay, so the advantage of including punctuation is I know I'm at the end of a sentence, right? Or I know I'm excited because there are exclamation points, right? Or I'm angry or something like that. But the disadvantage to doing it is, again, I'm going to have fewer intersections, right? I get, and so with shorter things, with shorter pieces of text, say like a tweet, I may want to try and have more intersections. I may want to specify things less, map more things onto the same element in the set. And for longer things, I might want to distinguish them more. Or I might want to say some punctuation is important, some is not. Right? If someone uses 5 exclamation marks instead of 1 exclamation mark, maybe that doesn't make a difference. Maybe I want to collapse all those together. There are lots of choices like this with punctuation, which is tricky. So, another thing like this would be like if I'm doing tweets or something. Now a lot of language has like emojis in it, right? Do I want to use emojis in here, or do I want to ignore them? I don't know. I had, like a couple years ago, I had an existential crisis because I didn't understand the point of emojis. Like why were people using them? Maybe it was just me getting a little bit older. Now, like, once I thought about it, like, and it is, does anyone know why there are emojis?
Well,
oh, okay,
I
good.
can just describe one situation. It's not like you have to use it extensively, but then when you have a business conversation and when you have ask some question or like something, some affirmative sentence, the person can interpret that emotionally with a negative context. But if you add a smiley face at the end of it, it means like you are positively asking that question. So it kind of conveys the intonation. That's what it probably, that's what
right.
helps
So the emoji, I think, comes from like emotion or the emote, right? You're trying to add this sentiment or other things that would be given by hand gestures or the tone of your voice over these texts. And so that seems like it could be really useful, but it might be tricky as well to incorporate. Yeah.
They're efficient.
Oh, they're
a lot with little.
Okay. I have not gone to that. I have not gone to that level yet, but that's good too. So it's so they're more like hieroglyphics, right? And that you can tell a story. Yeah. That's good too. So I've seen research projects where people try and like incorporate emojis and learn what emojis mean in various ways, and it can be entertaining, right? So there are lots of modeling choices here too, right? So far I've told you, okay, you can use Jaccard Similarity, and you can do this by doing Keygrams, but there's been this combinatorial explosion of different options you could have made, and they should kind of give fairly somewhat consistent things, and that similar sentences or documents should still be more similar than ones that are further away. But how it ranks things in between is going to change, and that's going to affect some of the algorithms you run, and it's going to affect some of the predictions you make, using this data. And there's not necessarily a right or wrong answer to some of these questions. Okay, so this is gonna we're not going to kind of dwell on this every lecture, but this is an important point, right? Don't think just because I chose this algorithm and I chose this distance function and I chose this way of modeling text means that's the right way of doing it, right? And for one point, don't think that means it's going to be unbiased, right? There's some implicit bias in how you're dealing with this, and we'll mention this in kind of a little bit more detail throughout the class as well in a few places. All right. Okay. So let's try and bring this back all together. Okay. So now what have I? Okay. So now I'm looking at two word grams on this set. Instead of treating them all as one set, I'm going to treat them as 4 different documents here. Okay? And so now I've converted these documents into sets. Okay, so I've made a modeling choice, right, to go from these 4 documents into sets. Okay, so this is a reasonable way to model them. But now that I have sets, I can calculate the similarity between them. So let's kind of go through these. So I'll use the Jaccard similarity. Yeah, and so the Jaccard similarity between document 1 and document 2 is going to be 1/3. Right? If this was going to be word vectors, bag of words, these are going to be identical, right? They have the same words in them. But the Jaccard similarity says that this value is only 1/3. The IM is the same, but am-sam and sam-I are different. Those both add to the denominator, but not the numerator. So I get 1/3. It's clear? Let me write it down. Okay, so the Jaccard similarity between document 1 and 3 is going to be 0. Turns out they both have the word I in them, but they have nothing else in common. So that's, I say, those are effectively as far apart as I care to model. Okay, it's not saying there aren't other things which are even further apart, but these have not sufficient similarity for me to care about them being similar. And in this context, these 4 documents, that's fine. 1 and 4 is going to have some similarity. I am is in both of them, but there's a whole bunch of other stuff. Okay? Document 1 and 2 and 1 and 4 both share one element that they're the same on, but because document 4 is much longer, it's going to be much less similar to document 1 than document 2 was. Okay? So the length now adds to the denominator and makes it less similar. Okay, and so here, the rest of them, document 2 and 3 is also 0. 2 and 4 is actually, has 2/7 similarity, which is not bad either. They have they both have sam, I am. So all of document 2 is repeated within document 4. But document 4 is a bunch of other stuff too, so the denominator is still 7. But that's reasonable. And document 3 and document 4 also has a lot of similarity. The I do not, and not like, right? This common theme of these 3 words is repeated. Okay, and so we can kind of see 1 and 2 are fairly similar, and 2 and 4 has a repetition, and 3 and 4 has some repetition within it. So I've captured that similarity. Okay, so I've said the maximum similarity was 1, and none of these get even close to 1. Okay, these are all, the largest one is 1/3 I've gotten here. This is not uncommon. Okay, so things that are not kind of near copies of each other, for Jaccard similarity, even with larger documents, is probably not going to get all that large. Okay, so in the homework assignment, you're going to get things that some are going to be fairly similar to each other. So you're going to see larger, but most documents are going to be pretty far away from each other. They're not going to have 0 similarity because they're not going to be so short probably, but if you look at documents on the web, there's going to be a bunch of common words which are used, and I guess if they're both in English. If one's in English and one is in Spanish or Portuguese, then they're probably going to be much further apart. Maybe Spanish and Portuguese will have some kind of overlapping sayings, but probably not too much. Okay, so this is not an uncommon sort of thing, even with larger documents, to see numbers this small and it still be useful. Right, I've still captured which documents are more similar than other ones. I've kind of brought those out with the higher similarities. Okay, so this basically makes sense as a distance between them. Okay, and so the first search engines on the web used like essentially a version of this to kind of say you had a keyword search. We'll talk about this in much more detail. We'll have a full lecture on search engines essentially later in the semester. But they start you type in something in the search bar, and then it would convert that into kind of some Keygrams like this, and there was a lot of kind of finagling in how it did the Keygrams and the modeling to try and get this to work well. And then it compared that with the documents on the web and returned the most similar ones. This is how the first search engines worked. Okay, and and we'll they were quasi-effective, right? And then they've gotten much better, right? But this is kind of the basis of large-scale text understanding, converting them into this abstract representation, and then we have a well-defined distance or similarity on it. And we'll see over the next 2 lectures how to make this very scalable. Okay. Okay, so 10 or so minutes has become very popular in these so-called word vector representations. Okay, and so this is kind of the default starting point when modeling text. There are only like 5. This idea is only, well, the idea is probably only older than 5 years old, but there are kind of a couple papers that came out about 5 years ago that kind of really changed how people analyze large-scale text and model large-scale text. And the idea, this is going to be a vector representation. And basically, instead of thinking about a whole document as being some object like a set or a vector, each word, like the word green, is going to be represented as some sort of vector. Okay, so it's going to be, and so it's going to be some vector, say v green, and it's going to be in, say, 300 dimensional space, or the most the fanciest one nowadays use like 1,024 dimensions. Okay, but there's say some pretty high dimensional space. Every word is going to be in this representation, and then when I talk about a sentence or a document, I can analyze the meaning of it now instead of I can understand something about the meaning of the document by looking at which words are in it. And I can understand the meaning of the individual words. Green and blue are probably going to be near each other in this space because they're both colors. Okay, and there's other things like if you look at 3 vectors, v king, v queen, v man, and v woman. If I look at these four words, and I do some like vector operations, I do v king plus v queen, or sorry, maybe minus v queen plus v man is going to come close to the vector for woman. So I can kind of do vector operations sometimes on these words, and so I can treat them like vectors in some regular vector, in a linear vector space. Okay, so this has become very common, or something kind of like this. Okay, so I'm going to give you kind of a very high-level overview of how these are created. The actual process is going to be a fair bit more complicated, and there's several variants of it, and eventually the kind of one of the last steps is to throw it into a deep net, and then they extract some layer out of the deep net, but kind of get sort of the word do, there's a 1 here for the word and, whether it includes likes or not, it's not important. It's going to have 1 for the word not, and and so forth. Okay, so it's looking, this instance of this word is going to get this representation, where it's just like the bag of words representation. I'm counting in this neighborhood of a radius 3. I'm going to count how many instances of each word. But if you notice, the word like is occurring twice here. So I'm going to get 2 representations of the word like. So this will be version 1, and this will be version 2. Right? And this one's going to have something different. It's going to have the word, it's not going to have the word and, but it is going to have the word do, and it is going to have the word not, right? And it's going to have some other different words in here. And so over some set of documents, I went to learn kind of a single vector that represents like across the English language. And I'm going to scan through all these documents and do this, you know, thousands, millions of times. And I'm going to take the average. Right? I'm going to take the average of these. Like, so this will be the overall vector. And then just with this case, I'll get a 1/2 here. This 1 occurs in both, so the average is 1. The average is 1 for not. And, you know, the zeros average out to be zeros. Okay, so I'm going to create this for every instance of the word like, create a vector, and then take the average of these vectors. Okay, so this continues. This is the continuous bag of words model. There's also kind of a similar model to this, which is doing something pretty close and kind of effectively fairly similar. And it's going to start with this representation, and then it's going to it's going to use a kind of a statistical distance between these vectors, which is not Euclidean, and it's going to compress it down to this vector is going to be super long. It'll compress it down to 300 dimensions in some way, and this will be the ultimate representation. But this is kind of the core of what's going on here. So these ideas of bag of words and Keygrams, you can kind of mix these together, and this was found very effective in this context. So most kind of deep nets and so forth that model language start with kind of a representation of one of these GloVe or these word-to-vec vectors, which are trained on as much of the internet as they can find, right? So on enormous data sets, they train these representations, and this is kind of a starting point for language analysis nowadays. So, okay, so there's a little bit more detailed example in the notes, but I think I'll stop here. The lecture on Wednesday is going to look at how do we use hashing together with this to start to speed this up. And it's going to be, and then we're going to need one more lecture the following week to really see how to put it all together. But we're going to combine this with hashing in the next lecture. And so if you have questions about the homework or anything else, so I have to run, but Harshini in the back will be around for questions.
Quick question for you.
Yep.
What is the proposal?